Okay, so first we only have two things left, I think. Just a quiz a week from today and the final. So the last quiz is Thursday. What would that be? 5, 6, 7? What? The last day of art class, yeah. And then exam 5 is Thursday, 12/14. Q in 13/26 here. And remember that that's cumulative. Yes, it is at 11. That is a different class I'm thinking of. Not PM anymore. Yeah, I mean, it'll be sort of like the other ones. It'll probably be half new stuff, half old stuff, that kind of thing. Yeah. Any questions about the end of the semester? And I mentioned last time, you know, I'm very willing to make other accommodations if, yeah. So just talk to me if that's difficult for you. All right. Any homework questions? I put up the homework sort of late. I did put up a couple problems, but you might not have had a chance to look at it yet. Okay. Well, let's do one of them. So entropy number 1. Anybody have it? All right, so the problem says a gas initially at, so a gas expands in an isothermal internally reversible process. It starts at P1 of 14 bar. And temperature 1 of 60 degrees Celsius. And the process takes it to pressure P2 of 2.8 bar. How do we know the temperature there? What are we going to have to do to calculate that? Isothermal, right? So this word allows us to calculate that T2 is also 60. And it says determine the heat determine the heat transfer and the work if the gas is, there are two cases. One is refrigerant 134A, and two is air treated as an ideal gas. And when you see stuff like that for gases that we've dealt with a lot, it should pop into your head that we can use tables. So if we can figure out what state it's in, we can look up specific volume, specific enthalpies, specific entropy, all these different things. Okay, so now let's think about what we know. So these entropy problems pretty often are going to use, so when we were doing problems in the first law of thermodynamics, which is what we've done most of the time, there was pretty much just one equation to use, and you could look at different forms of it or whatever. With these, most of the time, you're going to need the first law and the second law, and you're going to have to use them together. Okay, so that might not always be the case, but be ready for that. So what do we know here? We know that the first law says is it, well, we don't know anything about the internal energy. So the change in internal energy is equal to the heat added minus the work done. This is a closed system. And then what else do we know? We know that T ds is equal to du plus P dV. And we know the other one, T ds is equal to dH minus V dP. And okay, so we know the starting and ending pressures. We don't know anything about the volumes. Well, we can look up anything because, well, at the start and end point of this process, we can look up enthalpy, volume, all that stuff. So let's think about, and we know that the temperature is constant, which means that if we're going to integrate one of these TDS equations, we don't have to integrate the temperature. So that's sort of appealing. Let's VDP. We don't know. So let's take this first one and divide both sides by the temperature. So we get du over temperature plus 1 over temperature times PdV. And then let's integrate it from state 1 to state 2. We can pull the temperature out of the integral. So 1 to 2, 1 to 2, 1 to 2. PDV. This becomes, so integrate this, you just get the change in specific entropy. This one you get the change in internal energy over T, and that's all stuff you can look up. This is stuff you can look up. So it's looking good. Then you have 1 over T times, what's this integral? That's the work, yep. That's W. So this is W over T. And the table gives you, you can use that for the change in entropy. Just look up, that's just going to be entropy, specific entropy 2 minus specific entropy 1. You can look up the specific internal energy change. We know that T is equal to 60 degrees Celsius. Well, that has to be, you have to do that in Kelvin. So 333. And so that'll let you solve for the work. And then the heat transfer. Right, yep, so now the first law, right, exactly. You might have to do it as a, like per mass. So we have the change in internal energy is equal to Q minus W. This is all PDV, so this is actual work. That's not work per mass. So you got to worry a little bit about the mass in here. You know what? So delta U is equal to the mass times delta little u. But then you can, mass times delta little u is equal to Q minus W. So solve for Q. I don't think it gave a mass. So your answer is going to have the mass in there. Yep. Oh, yes. Yes. You're right. Yep. So this is, so this gives you work per mass. Yep, that's exactly right. And so then, I don't know. Let's erase this. But that's the sort of flow of it anyways. You have to think a little bit, just be careful about like when you have masses and when you don't. In the tables, you're always looking up specific things. So in any problem where you're using the tables where it's asking you for extensive properties, you're going to have to fiddle with the mass. Yes. Yes. Mm-hmm. But if you were cool, you would just derive them. Yeah. Okay. Oh, for part B, you mean? Oh, okay. Well, you could use the ideal gas table for air. I think I've given you that, haven't I? Have I not? Oh, well, uh, there's a so there's a table. Yeah, there are separate tables for a bunch of common gases when you're treating them as ideal gases, and air is one of those. And you can look up those values. I'll get that on B2L. Any other questions about that? All right. I don't know. I don't know too much about where these came from. I know he did think about that stuff a little. I know there's the Newton's law of cooling is an important part of sort of a beginning point for heat transfer, but I don't know how much of it he did. I think that stuff's really interesting, but I don't know anything about the history of thermodynamics. Mm-hmm. Yeah. Yeah. Uh-huh. Yeah. Yeah. Totally incredible. Totally impossible to imagine. Yeah. Okay. So last time at the end of class, I talked about um, the entropy balance for a closed system. You can think of this as uh, the second law of thermodynamics. Um, the basic idea was the change in entropy is equal to the net entropy transferred into the system plus the entropy produced. Bless you. And the entropy produced has to be greater than or equal to zero. Uh, that's a statement of the second law. Um, and so mathematically, you can write this as the change in entropy, S2 minus S1, is equal to the integral from state 1 to state 2 of delta Q over the temperature going all the way around the boundary, plus this sigma. And this sigma has to be greater than or equal to 0. Um, we don't know anything about the change in entropy. That can be positive or negative. Remember that like a refrigerator, any refrigeration system is a case where you're doing something that's making the entropy of your system go down. But there's entropy produced. It's not enough to make this, it's not enough entropy produced to make this positive inside the gas in the refrigerator. But if you added up the change in entropy of the system and the surroundings, it would have to be positive. Yes. It's actually the opposite of that. So you start out with that sigma cycle, and then I don't think I could make it through the derivation, but yeah, that's how you derive this. Is you start with that cycle thing, and then you break up the cycle into one process going from 1 to 2, and one going back from 2 to 1 somehow, and Um, okay, so let's do an example using this. Oh, and then one other thing before I start this example. When is that sigma 0? That's right. If it's a reversible, internally reversible, so your system is reversible, doesn't matter what's going on outside, that sigma inside your system is going to be 0. In any actual thing, that's going to be positive. So let's say we have an insulated piston cylinder assembly. And what we're dealing with is water. And it starts as a saturated liquid. At 150 degrees Celsius. How can you have saturated liquid water at 150 degrees Celsius? High pressure, yep. And then a paddle wheel inside changes this to a saturated vapor. As the piston moves freely. And we want to calculate first what's the net work per unit mass. And second, what's the entropy production per unit mass. Okay, well, the first law says change in internal energy is equal to Q minus W. It's insulated, so there's no heat transfer. And so we know that the negative, well, the work divided by the mass, that's what we're trying to find, is the work per mass, is equal to negative, 1 over mass times the mass times U2 minus U1. And so the work per mass is equal to negative specific internal energy minus specific internal energy at the start. We're trying to find the net work. This is water. We know the temperature and we know it's at saturation, so we have everything we need to look this up. So a table tells us that U1 is 631.68 kilojoules per kilogram. And as a saturated vapor, it's 2559.5 kilojoules per kilogram. And so the work per unit mass is equal to negative 1927.82 kilojoules per kilogram. So is the paddle wheel doing more work than the expansion of the gas does on its surroundings, or vice versa? The paddle wheel is, so we have net work being done on the system, and so the paddle wheel is doing more work than the system is doing on the surroundings. And then the second one, we want the entropy production. So we know that we're going to use the change in entropy is equal to the integral from state 1 to state 2 of delta work over temperature all the way around the boundary, plus the thing we're trying to find, the entropy production. What? Delta Q, yes, sorry. Ooh, that would have made it easier. The temperature, okay, so the temperature is 150 everywhere. So we can think of this as the change in entropy is equal to the heat added to the system divided by 150 degrees Celsius is, what's that, 423? And we can rewrite this as the change in specific entropy is equal to the heat per mass over 423 plus sigma per mass. That's what we're trying to find. And well, this, so what's the heat transfer into our system? 0, because it's insulated. And so we can look up these specific entropies in a table. S1 is 1.8418 kilojoules per kilogram Kelvin. S2 is equal to 6.8379 kilojoules per kilogram Kelvin. And so sigma over mass is equal to, subtract those two, and you get positive 4.9961 kilojoules per kilogram Kelvin. So in these kind of problems, I guess I would say, you know you're going to be using that entropy balance equation, and be ready to plug in, other variables that you can get from the first law of thermodynamics too. The first time you get an equation with more than one variable, that should be the thing you think of using the first law. Mm-hmm.
Can I go ahead?
Yeah.
Okay. Well, it's just something I've been sort of wondering since we started
Mm-hmm.
talking about it.
Yeah.
I mean, in all the mathematical formalizations, it's conceptualized as, heat or
Yeah.
temperature.
Mm-hmm.
How does this relate to probably the notion that we've all been exposed to that it's a measure of disorderliness of a system?
Actually, I think, well, if you think about it as, so heat only, I'm going to say essentially a thing that I said once before. If you think of the fact that heat only transfers from a high temperature to a low temperature, and things are most orderly, most useful for creating work when all the heat is stored in one high temperature reservoir and you have a energy free reservoir. Every time heat goes from your ideal super hot reservoir to your ideal super cold 0 Kelvin reservoir, you're messing up your most efficient possible case. So like if you take heat from this billion-degree reservoir and put it over to this 0 Kelvin reservoir, how are you going to ever get that energy back to do work in the future? You need to find, now you have this reservoir that's at 0.0001 Kelvin or whatever. You're going to find a colder reservoir than that, to use to get work out of it. So that's the way I think about it.
I guess maybe this will be being high energy corresponds to more disorderliness because it's more random motion.
I think of the orderliness as being how difficult it is to produce a heat engine. How difficult it is to turn that thermal energy into work. And if you, the two extremes are, so say you have 1,000 joules of thermal energy. The two extremes are, it's most useful for producing work if all of that energy is in one reservoir and 0 thermal energy is in the other one. And it's least useful if you just have one homogeneous thing. You can't do anything with that. Even though you still have 1,000 joules of energy, you can't use it. Yep. For the production of entropy, right. Yes. It can be anything. I don't think there's any kind of maximum value. Well, I guess if you think of like anytime you put through heat, you put thermal energy into something close to absolute 0, you have close to an infinite, it approaches an infinite change in entropy. So I don't think there's any limit on it. So now, question. Why would we ever want to know how much entropy is produced in a process? Why would it be useful to find that entropy produced in a process? That's a rhetorical question. I'm going to tell you. Yeah. So if you can break up some kind of cycle or something, some machine you're using into individual processes and calculate the entropy production on each one of those processes, the ones that have very high entropy production are the ones that you can think of as the best candidates for efficiency improvements on. If you have two parts that produce very little entropy and the third one produces almost all of it, then that third process is the one that you want to look at. So processes with high entropy production have many or big inefficiencies and are likely to be good candidates for efficiency improvements. Mm-hmm. Yeah, it's the exact same thing. Yes, that's right. Let's just do another example. This is pretty much the same idea as the last one. But let's say we have a gearbox in steady state operation. And so there's a rotating shaft coming in, providing work to the gearbox, and then a rotating shaft coming out that's work that the gearbox is doing on the surroundings. The power in is 60 kilowatts, and the power out is 58.8 kilowatts. And the temperature at the boundary of the gearbox is 300 Kelvin. And we want to know what's the entropy production inside the gearbox. The things that we're likely going to use are the first law that says everything was given as rates. So I'm going to write the first law as dE dt is equal to Q dot minus W dot. And this is steady state. So we know that Q dot is equal to W dot. And then the second law of thermodynamics says the change in entropy, I'm going to write this in the differential form. So ds dt is equal to the integral from state 1 to state 2 of delta Q over T going around the boundary plus the entropy production that we're trying to find. Just like this is 0 because it's a steady state case, you know, any properties inside this steady state system have to be constant, and so ds dt has to be 0. Yep. Yes. Thank you. Oh yeah, I'm using. Okay, so yeah, let me think about that. What we want to do here is this needs to be. We can think of this as, so this is the form I think I gave it. The sum of all the ways that heat is entering the boundary, just add up all those rates divided by the temperature. Yeah, thanks. I was mixing, mixing and matching those two equations. Okay, so sigma dot is equal to negative rate of heat divided by the temperature. So now we have to figure out what that rate of heat transfer is. Our total work is equal, and we're doing this all as rate. Our total rate of work, and remember, you know, the sign convention says that this is the work out, is equal to, sorry, let me change this to a net, is equal to the positive work out rate minus the rate of work in. And so that's equal to, the work out was 58.8. The work in was 60. And so this is negative 1.2 kilowatts. And so Q dot from the first law is equal to that net rate of work. And so this is also equal to negative 1.2 kilowatts. And so sigma dot is equal to negative of negative 1.2 kilowatts divided by the temperature at the boundary, 300 K. And you get a value of 4.1 times 10 to the minus third kilowatts per Kelvin. Or positive 4.1 watts per Kelvin. So there's a lot of having to think through those signs carefully to get that right. There's a million ways to get that wrong. You have to, you know, there's signs at every step you have to be real conscious about. But if you do it right, if you ever see one of these sigmas come out negative, you know you did it wrong. So Mathematically, I guess I would say the reason is that we, somewhere back a couple weeks ago, we went through a derivation that showed the Clausius inequality. And those were just the, so that temperature specifically is the boundary of your system. Where did that come from? I would say maybe more than trying to think about like how it makes sense physically, just remember that we derived that Clausius inequality from the second law of thermodynamics, and that Clausius inequality is where the entropy, the definition of entropy came from. But as far as whether it's inversely proportional or proportional to the square, like I can't help with that at all, but it does make sense. Again, like what we were just talking about before is like, if you think about entropy as a measure of how hard it is to use the energy you have to produce work, then it makes sense that the higher the temperature, you put energy into something at a very high temperature, it's pretty easy to get that energy back out, because you can use anything as a cold reservoir with that to produce work. But if you put energy into something at a very low temperature, it's really hard to get work out. It's really hard to use that energy again to get work. And so intuitively, I guess that's the way I think about it. Energy is really easy to get out of something hot and really hard to get out of something cold. Yeah, it is exactly the temperature at the boundary of your system. Yes, and because entropy is a property, and steady state means any properties stay constant. These kind of questions always make me nervous. Okay, I'm ready.
I guess I always make the assumptions that the temperature is constant, but more generally speaking,
yeah. So for the problems, I think you must be exactly right about that. All the problems we're going to do are going to be sums of, like, the most we'll have is like 3 different boundaries with 3 different temperatures, that kind of thing, and then you just add them up. That's why the sum is in there. But somehow you can change it to an integral, but I'd have to think about it for a while. Yes, that's right. Yep. Mm-hmm. It can get a little tricky thinking through that stuff because of the deltas and stuff. Like, what does it mean when you, like, I don't know, when you're talking about a delta Q dot, But generally, you're right that I'm sure you can write it as an integral instead of a sum. Yeah. Any other questions right now? Okay. So this. When we're doing things in terms of energy balances, one of the things about energy balances is you don't know before taking measurements anything about the direction that a process is going to occur. Like when you use conservation of energy to talk about, like, you pull a spring back here and then it moves, and then when it's here, what's its speed going to be? You're having to know something about its location in order to figure out what it's going to be. And you don't have any way to say, you don't have any way to specify, like, is the thing going to start here and end up in your hand? Or is the thing going to end up in your hand and end up here? Okay. Energy balance doesn't let you know anything about the direction of a process. But now, finally, we're going to talk about how this entropy balance lets you figure out the directionality of processes. So so if you're dealing with an isolated system, and actually this is exactly a question you asked last time. So here is what it means for a system to be isolated. No material transfer across the boundary. Across the system boundary. And no energy transfer across the system boundary. And for any isolated system, so this is true of the universe, but it's also true of any system that's isolated in this way. Then for an isolated system, the change in entropy, this is the notation that they use in the book. So the change in entropy for the isolated system is equal to this produced entropy for the isolated system, where sigma isolated is greater than or equal to 0. So this is basically the second law of thermodynamics. It says that entropy can only increase if your system is isolated, whereas before we kind of had to take everything into account. Now we're saying what we can do to look at a small chunk of material. Okay, so how is this going to let us figure out the directionality of? So what we can do is we can use the first law of thermodynamics, the energy balance, to figure out two states, and then we can use this entropy balance to figure out which of those states has more and which of those states has less entropy. Whichever one has more entropy is the thing that happened later. You can't go back to the original one if it's still isolated. Okay, you could go back, but you have to do it by hooking up compressors and all this, just like in a refrigerator, you're going to less entropy, but you have to do it with a compressor and all this other stuff. Yes, that's right. Yep, exactly. Yep. Yeah, Stephen Hawking is says some very weird stuff. But I read some just layperson's Stephen Hawking book, and it was he was talking about how really space and time might just be one single thing, and then he's like, well, but why do we? And it's we're living in this 4-dimensional space all the time, and then he said, so why do we have a sense that things are happening in a sequence of instants as opposed to just perceiving time as another dimension. And he said maybe it's because, you know, the processes in our brain, what we perceive as forward time is our brain's increasing entropy as these processes happen, and that's why we like perceive a succession of things to be the increase of entropy. Like it has to do with the directionality of entropy production in the things that make us perceive things, that only makes us perceive time moving towards increased entropy. So I'll probably have an essay question about that on the test. Just make some sense out of that. But okay, so this is cool though. I mean, like this is something that, you know, this is a gap in your ability to do calculations that you've had up until now, and now we can fill this gap. So so let's say that we have an isolated system, like what I'm talking about is an insulated, like fixed tub that holds water with a metal bar inside the water. So 0.5 kilograms of steel at a temperature of 400 degrees Kelvin. And it's sitting in 10 kilograms of liquid water. At 283 Kelvin. This is a solid and a liquid. We're going to make the assumption that the specific heat is constant. So remember, so we'll assume incompressible. And so the specific heat for water is 4186 joules per kilogram Kelvin. And the specific heat of steel is 460 joules per kilogram Kelvin. And we're going to do two things. First, we're going to figure out what's the temperature of the system when it's at equilibrium. And second, the question is, how do we know that it goes from the different temperatures to equilibrium and not equilibrium to those different temperatures? Think how trippy that would be if you put two things at 25 degrees into contact and you came back and one was like frozen solid and the other thing was steam or whatever. Yeah. So hopefully this answer will agree with our understanding. Okay, so these are the specific heats. How come I didn't specify CP or CV for these? Incompressible, that's, yep, those are the same thing. And if it's incompressible, then C is just equal to du dt. And so du is equal to C dt, or delta specific energy is equal to C times delta temperature. And that means that the change in internal energy is equal to M times C times delta T. And you've probably seen that formula before, but and so now what we're going to do is use the first law. And the first law says the change in internal energy is equal to the heat added to the system minus the work done by the system. In an isolated system, these both go to 0. So the change in internal energy is 0 if this system is isolated. And the change in internal energy is the change in internal energy of the water plus the change in internal energy of the steel. Those have to add up to 0. So we have the mass of the water times its specific heat times the change in temperature. We already know what those different temperatures are. We're trying to figure out what the temperature is when they have the same temperature. So I'm going to write this as T final minus, for the water, it was 283. It's an isolated system, and an isolated system has no energy transfer yet. Right? That's right. So yeah, this is because it's isolated. And then plus the mass of the steel times its specific heat, 460, times T final minus its starting temperature, which is 400. And those have to be equal to 0. And so you get 41,860 TF. Multiply those for me. I sort of suspect maybe I multiplied it wrong. Yes, so 4186 times 283. No, 41,860 times 283. Yeah. What is it? Okay, 1.18. What was it? That would actually make it worse than what I got it. Okay, so 1.1846 or something times 10 to the 7th. And then this one is 230 TF minus, what's this one? 92,000. Even? Ooh. Is equal to 0. And so then you add these two TFs up, you get like 42, 90. TF is equal to, and what do you get for these? What is it? 1.137? That's a lot of round off. 1.1938. Okay, times 10 to the 7th. And then what do you get for TF? Okay, that's even worse than what I got. 283.6 Kelvin. Okay, well, I guess that wasn't very much metal, and you put it in a lot of water, and so you end up with basically, it comes out to be the water temperature. Okay, so now what we have is just two states, but there's, so far we don't know that one happened spontaneously from the other one or whatever. But now what we need to do is use the entropy balance. So we know that you can think of it this way. The change in entropy, actually, let's just, I have this formula here. The change in entropy for an isolated system is just equal to sigma for the isolated system. And so the change in entropy for the water plus the change in entropy for the steel is equal to sigma. And this is an equation from a couple days ago. If we assume this is incompressible, then the change in specific entropy is equal to C times the natural log of T2 over T1. And so just add both of these two up and multiply them by, so the change in extensive entropy is the mass times C times the natural log of T2 over T1. And so we have 10 times 4186 times natural log of 283.6 over 283 plus 0.5 times 460 times the natural log of 283.6 over 400. And what do you get for that? But let me set up the other one too. So this would be the one that's going towards equilibrium. How would this work if, so we're basically going to test the two directions of this process. How would it work if we wanted to test the one that goes from equilibrium to the two different temperatures? The only thing that would change is that we flip these, you know, which one we call T1 and which one we call 2 flips. So we'd have 10 times 4186 times natural log of 283 over 283.6 plus 0.5 times 460 times natural log of 400 over 283.6. So can you calculate that one too? This is away from equilibrium. So anyone who gets one, tell it to me. 9.558. This is in kilojoules per Kelvin. And this is negative 9.558 kilojoules per Kelvin. So if you have this thing happening spontaneously in an isolated environment, then you know it goes from that different temperatures to equilibrium, and that can't happen. Any questions? Okay, that's it.